All right, so I want to talk about the principle of a generator, which is also the principle behind a motor or electric motor. A motor is a generator in reverse, um, which relies on the inductive effect that we've been talking about so far in class. So specifically, I want to talk about a generator that's based on a static magnetic field. Okay, so let me um, draw what I'm going to discuss. So we're going to have um, a loop of wire that can rotate. Okay, and we'll have some electrical contactors. So one side of the loop will contact say a circular contactor here. I'm not drawing that very well. Let me try again. Okay, there's going to be a contactor that kind of is a ring. It looks like that this contactor will connect to as it rotates. It will slide along, and another one here. Okay, so that this thing is always in electrical contact with that ring. And then if I can connect this to a circuit, let's say I have a light bulb over here. Okay, um, and then I have some kind of hand crank here that I can turn. So I can basically make this spin at some angular frequency by turning it, and this will cause the whole apparatus to return. So if I have a rotation that looks like this, that means that at this instant, this side of the bottom side of the loop is going into the page in its velocity, and the top is coming out of the page, right? So it's spinning in the sense that I've drawn in this vector, that angular frequency there. Okay, and then I imagine that I put some magnetic field in this region here. Okay, that, everywhere where the loop is. So, the interior to the loop does matter, of course, when we talk about the flux through the loop, but the physical mechanism. So we're going to generate an EMF here that's really a motional EMF. So in this loop, there will be a motional EMF, if I can write that. Okay, so again, this will be due to the V cross B forces on the electrons in the wire will tend to cause an EMF, tend to cause the electrons to, as we'll see, to rotate through this loop. And so the idea is you generate an EMF that goes, let me pick another color here, that will say might be a net EMF, a net tendency again to push current around in this direction, and that will tend to drive current through these contactors, through the light bulb, and then back. Okay, and so by doing this, I can, light my light bulb, and this is exactly the same way that the lights in your house, the lights in the, wherever you are right now, are on because of this kind of generator. You don't have somebody turning a crank. You have a steam turbine, for example, in a coal plant, where you heat up water by burning coal or natural gas or possibly a fission plant, and that steam then flows through a turbine that causes rotation, rapid rotation of elements that are a lot like this. Okay, and then you might have permanent magnets that the wires rotate through to generate this motional EMF. Okay, and that's what powers your light socket. Okay, um, so we want to analyze this situation using what we've learned so far. Okay, so we want to calculate the EMF that's generated. Now this is going to be an alternating current, as we'll find out. So this is, as I turn the loop, the EMF is going to switch directions. Okay, but we want to calculate the EMF generated by this rotational process. And we know that the EMF, in the context of the chapter we're working on, will be due to electric and magnetic fields, okay, and motion. So we have two contributions. The first contribution, oops, that's supposed to be a DL. The first contribution is any electric field that has a non-zero curl, and that means electric fields generated by time-changing magnetic fields. This is the motional EMF contribution. So in this particular case, if in the lab frame as we look at this, we see no time-changing magnetic field. The magnetic field is static and the loop is rotating. So this term is going to be 0 in this case, and this term is going to be finite. This is where you're going to get an EMF generated. Now, if I switch to the reference frame of the loop, I'd have a different point of view. I would argue that the magnetic field is changing, and I would see an electric field due to that magnetic field. Okay, but for this situation, it's all motional EMF. Okay, but we don't necessarily care. We can go through and calculate this, and that's one way to get the right answer. But we know that in both cases, either if it's this term or this term, we can write down the EMF generated as just being minus d phi b dt. Okay, so all I need to do to calculate both of these contributions is to look at the change in the flux through the loop as this process happens. Okay. All right, so let me go to the next page here. If I have my loop, let me do this. I'm going to draw it two ways. I'm going to draw it. Now here's my loop, and let me just ignore all the associated, well, I do want to keep it open, okay, because I want to consider the EMF once around the loop. I don't have to keep it open, okay, I can make it closed. I want to consider the EMF once around the loop, okay. In reality, I'm going to open this up and connect it to a circuit, but that's not relevant right now, okay. I'm going to have this thing spinning. I'm going to have some hand crank here. It's going to spin like this, okay. And the magnetic field is threading through it like this. Okay, let me draw it from the side now. Okay, so if I draw it from the side, and again, this thing is rotating, so just to remind you, as it's drawn right now, this part is coming out of the page with a velocity v, and this is going into the page with a velocity v. Okay, rotating about this axis here. All right, so if I draw it the other way. Now let's look from this side here. Oops, from this side. So as if I'm, my eye is looking that way. What I will see is, and let me take it at a tilted angle, so it's not straight up and down, but the loop is kind of at an angle. Okay, so I'm looking at the edge of the loop. The loop goes into the page. The magnetic field, let me use a different color. Okay, the magnetic field is going to go like this. Okay, all right, and so I want to evaluate this expression that tells me the EMF is just related to the change in the magnetic flux through the loop. Okay, to do that, I need to make a couple definitions. I need to pick, for this side of the equation, a normal vector to my loop. So I have to pick a loop, first of all, and that's well defined. That's the actual loop that I'm rotating, this loop of copper wire. And the surface, I can pick, again, infinitely many surfaces are bounded by that loop. Again, think about a soap bubble. I can blow it to various sizes and it's still connected to that loop at its ends. But let's just take a soap bubble that's flat, okay, a surface that's flat. It's an imaginary surface. We'll take that imaginary surface, and now all the signs here are defined by my choice of normal vector, okay? So let's pick a normal vector that goes this way in this drawing. Okay, so there's n hat. Now if I do that, that makes this EMF be defined as going in the right-hand sense. So when I say EMF, there's an electromotive force, a tendency for current to flow. And so if the EMF is positive, it will flow in a certain direction that's defined by my choice of this normal vector. Now, just to be clear, it's not as if I choose a different direction, I get a different answer in terms of what actually happens. The current will flow always in the same direction, no matter how I choose my normal vector. It just turns out the definition of positive and negative is connected to how I pick this normal vector. So, if I find that the current flows like this through the wire and around the circuit in that way, that might be positive if I choose a certain normal vector. It might be negative, but it doesn't mean that the current is changing direction. The current will go in a certain direction based on the physical situation. But whether or not you call it positive or negative depends on your choice of normal vector. Okay. So if I happen to pick a normal vector that's like this, I use the right-hand rule, which I can't show you. I guess I could turn on the camera. Well, anyway, let me just say this. The right-hand rule is that I put my thumb in the direction of the normal vector and then wrap my right hand my fingers in my right hand will go with the direction around the loop that current would flow with a positive EMF in that frame. And that's actually going to be opposite of what I've drawn here. Okay, so if I look and complicate my drawing here, I'm going to look from above now. So here's my normal vector coming out of the page. What that means is that if that's the normal vector that I choose, when I find a positive EMF, that means current's going to flow like that. That's a right-handed loop that has, if I point my thumb upward, my right hand will loop around like that. Okay? All right, so that's just getting the signs right. But now let me actually calculate the EMF. So what I'm after is the EMF. That's all I care about, because that's not all I care about, but what I care about at the moment is to try to calculate how much EMF turning this loop generates, and that's going to tell me the current that flows through my light bulb. Okay? So EMF is minus d phi dt, so it's minus d dt of the integral of b dot dA. Okay, and I can rewrite this. Okay, b is constant, so it doesn't vary in space. So I can write this as b dot n. This I can do even if it's not constant. Okay, but I can pull out the this kernel of the integral because that's constant. So b is constant. N hat is constant in space. Now it's not constant in time. Okay, but if I'm doing this integral over the area, the normal vector always points in the same direction everywhere on the surface. Okay, because I picked a planar surface, and so this is constant over the area, not constant in time. Okay, so I can pull it out of the integral. I get negative d dt of b dot n times a. Okay. All right. Let's see. Can I squeeze it in here? And so I tell you what. Let me go to the next page. Before I go there, let me just do this on this page. So b dot n hat. Okay. So if I go up and look at my drawing again, so I'm going to define an angle theta. That's going to go between the direction of the magnetic field and the normal. So let me just go up here and redraw a normal, okay, because the normal always points the same direction everywhere on the surface. The angle theta will be right here. Okay, so that's the angle theta. It's between the magnetic field direction and the direction of the normal. So if I define that angle theta, then this becomes b cosine theta. Okay? All right. So let me go to the next page now. So that means that my EMF is going to be minus ddt of b times a times cosine theta. Okay. Now, the magnetic field is static. The only thing that's changing is the angle of the loop. And so the area of the loop is static too. So this just becomes minus b a times ddt cosine theta. Okay, and theta is changing in time, so I get minus b a. So the derivative of cosine theta, of course, is negative sine theta, right? So I get sine theta, negative sine theta, times d theta dt. Okay, and d theta dt has been defined for us. D theta dt, now the sign of d theta dt, we have to make sure we get right, okay? So the question is, that really has to do with your definition of positive or negative theta, okay? And so the magnitude of d theta dt will be just the angular frequency that we wrote down at the beginning, the rate at which you spin the loop. So that's really, d theta dt is really defined as that omega. So this becomes omega ba sine theta. Okay? All right. And, because I just defined omega to be d theta dt, we can write down that theta is going to be just omega times t. Now, there could be some starting theta naught. We can set that to be 0 to make life easier. Okay, just set that to 0. So the angle is just going to be omega times t. Okay, that's how you define this angular rotation rate. And so this becomes that the EMF is omega ba sine of omega t. Okay? All right. Now again, there could be a starting theta naught here, and we do have to be careful about the sign of d theta dt, okay, in terms of whether you spin it one way or the other. All that does is change the overall phase of the oscillation, okay? But what this results in is an EMF that basically oscillates in time up and down. This is just like the EMF that comes, or the voltage that comes out of your wall socket, okay? So if this happens to be that I rotate the wheel or the loop at 60 hertz, I'll get 60 hertz AC electricity. Okay, and again, this is exactly how electricity is produced. Well, the generator looks much more complicated, but the principle is the same. You rotate a conducting loop through a permanent magnet field, or sometimes you rotate the magnets through stationary loops. It depends on the arrangement, but both give you the same effect. Okay. All right, so that's the EMF generated by this rotating generator, and then this will cause a current to flow back and forth through the light bulb, and it'll light up. So if it goes at 60 hertz, you won't notice that it's going back and forth. You'll just see steady light. Okay, and the reason for that is that the light generated by the light bulb is because of its temperature. Okay. And so the temperature in the bulb doesn't change so quickly. When you basically you heat it up to a certain temperature and it glows. And by running current back and forth, you don't see the fluctuations in the light in that case. Okay, let me stop here.